Welcome to Architect of Tomorrow. We don't just write code here, we design the systems that run the world.
Welcome. In the next 45 minutes, I'm going to share something that will fundamentally change how you think about building artificial intelligence systems. Not about prompts, not about models, but about infrastructure. You see, we're standing at an inflection point right now in 2025. And the decisions you make, the architectural choices you commit to, these will define whether you're relevant in 2030 or obsolete. Think about this. In the next 5 years, the number of AI agents will grow by 100 times. Band window will explode by 81 times. Networks will saturate. Energy will double. And the paradigm will shift fundamentally, from bigger models to smarter inference. By the end of today, you'll know exactly what you need to learn, exactly when to learn it, and exactly why it matters. So, are you ready to become an AI architect for tomorrow? Let's begin. All right, let's look at the data. And this is where it gets real. Right now, in 2025, we're expecting 50 to 100 billion AI agents deployed globally. In just 5 years, by 2030, that number will explode to 2 to 5 trillion agents. Do you grasp what that means? That's not just growth, that's exponential explosion. 100 times more agents. Operating, learning, communicating in networks. Now here's the problem that nobody's talking about. Our networks, they can't handle it. Today, we're moving about 100 exabytes of data per day. Sounds huge, right? By 2030, we'll need to move 8,000 exabytes per day. That's 81 times more bandwidth. But the backbone network infrastructure, it's only growing at 5 times capacity. Do the math. We have a massive gap. And that's not even the worst part. The access networks, the edge gateways where your user is sitting, where your agent is deployed, those networks will be saturated beyond 70% capacity by 2030. Forget about latency, forget about reliability. We're talking about saturation. And all of this means the paradigm has to shift. From build bigger models to architect smarter inference. From centralized to distributed, from monolithic to mesh. Your infrastructure choices matter more than your model size. And if you get this wrong, no amount of clever prompting will save you. That's the inflection point we're standing at. Here's something I want to be completely honest with you about. On the domains you're currently good at, you're crushing it. You're at 89 out of 100. Foundation models, memory architecture, prompt engineering, you know this stuff. But here's the gap. For the problems you'll actually need to solve by 2030, you're only at 72 out of 100. Let me break this down. Look at these 4 critical areas. Multi-Agent Orchestration. You're at 80 today. You need to be at 98 by 2030. That's an 18-point jump needed. Safety and guardrails. You're at 88. You need 99. Guardrails fail on unseen attacks, dropping from 91% accuracy to 33% in adversarial scenarios. Observability. You're at 87. You need 97. But you're building black box agents with no visibility into what's going wrong. Enterprise deployment. You're at 83. You need 95, because 80% of deployments fail due to organizational, not technical, reasons. And here's what's declining in relevance. Manual prompt engineering. You're investing 90 out of 100 points here. You'll need 79 by 2030. Reasoning models will auto-optimize. Your clever prompts? Irrelevant. Single agent patterns. Foundation knowledge, yes, but the future is composition and orchestration. Chain of thought prompting. It's baked into the models. You won't need to ask it to think step by step anymore. So here's my question for you. Are you investing time in what matters by 2030? Or are you perfecting skills that'll be automated away? This presentation answers that question. Okay, so what do we do about this gap? Over the next 30 minutes, I'm going to walk you through the 6 critical missing pieces, the 6 topics that will make or break your relevance by 2030. These aren't abstract concepts. These are concrete architectural decisions, real technologies, real patterns, real problems you'll face. And importantly, most developers aren't even thinking about these yet. So by learning them now, you're getting a 5-year head start. Let's dive in. Let's start with the foundation. Agent operating systems. Think about this. How did we deploy applications before Docker and Kubernetes? Manually. Servers scattered everywhere. No consistency. No resource management. Total chaos. Then containers came. Suddenly, we had a standard unit of deployment. An OS-level abstraction. and the world of microservices became possible. The same transformation is happening to AI agents right now. Today, we treat agents like stateless apps. You call them, they respond. Done. But that's fundamentally wrong. Agents are becoming persistent processes. They need memory, they need scheduling, they need isolation, they need resource management. Enter AIOS, Agent Operating Systems. It's a kernel-like environment that does exactly what Linux does for servers. 1. It manages agent scheduling. Multiple agents running in parallel, competing for compute resources, without one blocking another. 2. It manages memory, both short-term working memory and long-term knowledge, efficiently across the system. 3. It sandboxes tool execution. An agent can't access secrets it shouldn't, can't call APIs it's not authorized for. Security at the kernel level. 4. It provides portability. Whether you deploy on edge devices, on-premises, or cloud, the agent runs the same way. Now ask yourself, who's doing this today? Who's managing agent lifecycle, memory, scheduling as a platform concern? Almost nobody. Everyone's rebuilding it in application code. By 2030, when you have 1,000 or 10,000 agents running in your organization, you cannot do this at application level. You need AIOS. And here's what you need to do this month to master this. Clone the AIOS repository. Study the kernel, the scheduler, the memory manager. Understand how it orchestrates agent execution. Deploy a multi-agent workflow in AIOS. Measure the scheduling overhead. Compare it against a monolithic approach. See the benefits firsthand. Containerize your agents. Build Docker images. Test portability across edge and cloud. Think operationally. What permissions does each agent need? How do you revoke access? Design capability models. 6 to 8 weeks. That's how long it takes to become competent in agent runtimes. And it's time well invested. All right, let's talk about something uncomfortable that nobody wants to discuss at conferences. Infrastructure is about to become your primary constraint. Not model capability, not algorithm sophistication. Infrastructure. Here's the hard reality. By 2030, edge and access networks, the networks closest to your users, will be saturated beyond 70% capacity. The peering points that connect continents? Even worse. We're talking 80-90% congestion. But the Tier 1 backbone, the main internet highways, those are growing more slowly. Why? Because they're expensive. You can't just build them overnight. So where will your bottleneck be? Not the internet backbone, at the edge, right where your users are, right where your agents need to respond. Now, agent communication is fundamentally different from HTTP traffic. It's bursty, it's asymmetric, it's timing sensitive. Imagine 10,000 agents all trying to coordinate a decision in under 5 milliseconds. And the network can only give you 20 milliseconds of latency. You've missed your deadline. And then there's energy. GPUs consume 20 to 50% of data center power, period. As models get bigger, they get hungrier. But data centers have power budgets. You can't just keep adding more. So here's the architectural implication. You cannot send all compute to a centralized cloud. It's economically impossible. It's physically impossible. You have to push inference to the edge. You have to think about energy-aware scheduling. You have to minimize data transmission because transmission costs energy. And here's what you must do. Use network simulators, NS3, Omnet++, to model bandwidth saturation. Run scenarios with 1,000 agents. See when coordination breaks. Design edge-first architectures. Critical agents near users. Coordination at regional hubs. Learning centralized. Profile your inference power consumption. Not just flops, actual watts per inference. Optimize your protocols. Stop using JSON. Use compact binary protocols. Batch agent communications. This is systems thinking. This is what architects do. 4 to 6 weeks to understand this. And it'll change how you design everything. Okay, here's something that's going to completely change how you think about model selection. For years, we've been operating under a simple belief. Bigger model equals better results. So we keep scaling parameters. 7 billion, 13 billion, 70 billion, 140 billion. But that's wrong, and the data now proves it. Recent research shows that a 7 billion parameter model with 10 times more inference compute using techniques like tree search, best-of-n sampling, and verification beats a 34 billion parameter baseline. Think about what that means. Same quality results, but smaller model, which means lower energy, lower latency, lower cost. Why is this possible? Because inference compute is different. You can batch it. You can run it at times when your data center has renewable energy. You can parallelize it. But training a bigger model? That requires power now. It's a one-time expensive operation. So the new paradigm is, don't scale parameters, scale inference compute. Imagine your system with different inference budgets. For routine decisions, summarize this email, use fast inference, one forward pass, ultra low latency, ultra cheap. For high-stakes decisions, approve this transaction, diagnose this patient, use expensive inference, 100 forward passes with tree search. Take your time, get it right. And here's what this means for you as an architect. Your model selection now has two dimensions, not just parameters, but inference strategy. When you're choosing models, you're not asking what's the biggest. You're asking what size plus what inference compute gives me the best cost accuracy latency trade-off for my use case. It's a completely different optimization problem. So here's what to do. Benchmark. Run Llama 7 billion plus tree search versus Llama 34 billion baseline on your domain. Measure cost per inference, measure latency, measure accuracy. Use inference frameworks, guidance, LLM-RS, VLLM. These let you implement structured inference, speculative decoding, verification strategies. Design tunable budgets into your agents. Fast path for routine tasks, expensive path for critical decisions. Monitor ruthlessly. Track inference tokens, track compute cost per task. Optimize the expensive paths. 4 weeks. That's the time frame to become expert in inference scaling. And it'll save your company millions while improving results. Imagine this scenario. You have 1 million agents in your organization. They're making decisions, coordinating, learning from each other. Now, how do you orchestrate them? Option 1. Centralized coordinator. One master node that decides everything, routes all messages, manages all state. But here's the problem. That coordinator becomes the bottleneck. Every single agent has to go through it. And if it fails, your entire system collapses. That's what we have today. Centralized orchestration. And it breaks at scale. Option 2. Agentic mesh. Imagine instead, agents that are peers. They don't report to anyone. They communicate directly. They discover each other dynamically. They coordinate through events and shared context, not through a central controller. Think of it like the internet for agents. No central authority, no single point of failure, just distributed intelligence coordinating peer-to-peer. Now, how does this work technically? First, you have an event backbone, Kafka or Pulsar. Every agent publishes decisions, errors, outcomes to this event stream. Every agent subscribes to relevant streams. Second, you have peer protocols. Gossip protocols like Surf or Raft. Agents discover each other. They reach consensus without a coordinator. Third, you have custom data planes optimized for AI traffic. Not generic HTTP proxies, but specifically designed for bursty, latency-sensitive, asymmetric agent communication. And here's the magic. Every interaction creates a trace. Every tool call, every error, every outcome flows through the event mesh. Over time, the system builds a compounding knowledge base. Agents learn from each other's experiences. Patterns emerge. The mesh becomes smarter over time. Now, I want to be clear. This is not easy to implement. You need to think about failure scenarios, network partitions, Byzantine behavior, consensus mechanisms. But here's why it matters. By 2028, centralized orchestration will be an anti-pattern. Teams that haven't built mesh architectures will be stuck. They'll be blocked from scaling. So here's what to do. Deploy Kafka as your event backbone. Get agents publishing and subscribing. Learn gossip protocols. Surf is a good starting point. Understand distributed consensus. Design custom gateways. Optimize for agent traffic, not HTTP traffic. Build emergent discovery. Let agents announce capabilities. Let others discover them dynamically. Instrument everything with tracing. Open telemetry. Every decision, every error, every outcome gets logged. 8 weeks. That's how long it takes to become competent in mesh architecture. And it's the architecture that'll dominate the next 5 years. Let me ask you a difficult question. In a mesh of 10,000 autonomous agents, how do you know which agent is authentic? How do you prevent a malicious agent from impersonating a trusted one? How do you enforce policies like only certified agents can access financial data? And here's the regulatory angle. How do you prove to an auditor that Agent X made this decision? That it was authorized? That it's accountable? In traditional networks, we had a simple model. Everything inside our firewall is trusted. But in an agentic mesh, that's wrong. You can't trust based on network location. You need cryptographic identity. Enter zero trust architecture, specifically for agents. Every agent gets a cryptographic identity, not a username, not an API key, a decentralized identifier, a DID. Agents register themselves with a DID, like didwebmycompany.com/agent/financial approver. That's a globally verifiable, cryptographically provable identity. Then, agents get verifiable CREMZs. Think of them as achievement badges. Agent X is certified for customer data access. Agent Y is authorized for transaction approval. Now, when Agent X wants to talk to Agent Y, here's what happens. Agent X presents its DID. I am DID Web. Agent Y verifies that DID cryptographically. Agent X presents its credentials. Here's my authorization to access financial data. Agent Y verifies those credentials against a revocation list. Is this credential still valid? Hasn't it been revoked? Only if both the identity and the credentials check out does communication happen. And here's the critical part. Every single interaction gets logged. Forensics trail, audit trail, for compliance, for incident response. Now, why does this matter beyond just security? Regulated domains, finance, healthcare, pharmaceuticals, will require this by 2027. Not as a nice to have, as a mandate. And if you're not thinking about agent identity now, you'll have massive technical debt when regulations hit. So here's what to do. Adopt W3C DID standards. It's not proprietary, it's open. It's becoming the standard. Start with DID Web. Agents get identities tied to your domain. Issue verifiable credentials. Design credential schemas for your domain. Financial approver credential. Customer data access credential. Implement Zero Trust Auth. Every agent-to-agent call, authenticate DID, verify VC, check authorization policy. Build a revocation system. Compromised agent? Revoke its credentials in minutes, not days. 6 weeks. That's the time frame to design and prototype agent identity. And it'll put you ahead of 99% of organizations still thinking about traditional security models. Here's a hard truth. Testing and guardrails catch about 95% of problems. But that last 5%? That could kill your company. Consider this. You deploy a financial approval agent. It has guardrails. It's been tested. You're confident in its safety. But then an attacker finds an adversarial prompt. It exploits a combination of conditions your tests never covered. The agent approves a $10 million fraudulent transfer. Now, regulatory investigators ask, did you prove this couldn't happen? And you have to say, no, we just hoped it wouldn't. That's not enough anymore. In safety-critical domains, medical diagnosis, autonomous vehicles, financial decisions, you need proofs. Mathematical proofs that the agent will never violate critical properties. Not probably won't. Period. And the tools exist. TLA+, SMT solvers, model checkers. They're used to verify distributed systems, protocols, aircraft firmware. Why? Because in those domains, failure is unacceptable. Now here's how formal verification works. You specify your agent's critical behavior in a formal language. TLA+ is excellent for this. You describe, financial approvals never exceed this limit. Personal data never leaves this region. Decisions never contradict this policy. Then you run a model checker. It explores every possible execution path, every possible state, every possible input combination. And it either proves, yes, this property holds in all cases, or it finds, here's a counterexample where it fails. If it finds a counterexample, you've discovered a bug that testing would have missed, and you haven't shipped it to production yet. That's the power of formal verification. Now, I'm not saying you verify everything. Formal verification is expensive. It takes time. It requires expertise. But critical workflows, financial approvals, data access decisions, access control, those you specify formally. Those you prove. And here's the timeline. FDA, NIST, AIRMF, other regulatory bodies are increasingly requiring formal assurance for high-stakes AI. Not today, but by 2026, 2027, it'll be expected. So here's what to do. Learn TLA+. Lamport's tutorial is free. Spend 2 weeks learning the notation. Write formal specs for your most critical workflows. What can the agent do? What cannot it do under any circumstances? Run the model checker, TLC. It'll prove your specs or find bugs. Add runtime verification. Deploy contracts in your code. Preconditions, postconditions, asserts. They won't prove properties, but they'll catch violations at runtime. Start with one critical workflow. Build the skill incrementally. Don't boil the ocean. 10 to 12 weeks. That's a time frame to become competent in formal methods. And it'll make your systems dramatically safer. And that's priceless. Before we move on, I want to share one more critical insight about agent design. Right now, most teams are building monolithic agents. One big model, one big context window. It tries to handle navigation, reasoning, interaction, execution, everything. And it works. Until it doesn't. Here's the problem. Monolithic agents are fragile. If one component fails, the whole system fails. They're hard to test because you're testing everything together. They're inefficient because they waste compute on tasks that don't need sophisticated reasoning. But compositional agents? That's a different story. Imagine instead, specialized micro-agents, each an expert in one domain. Navigation agent. Its only job? Figure out where to go. Is it a simple task? Fast, efficient. Interaction agent. Its only job? How to communicate with other agents or APIs. Reasoning agent. Its only job? What to decide given complex inputs. Execution agent. Its only job? Implement the decision. Now here's the architecture. These agents compose dynamically based on the task. Simple task? Route to navigation plus interaction. Skip reasoning. Ultra fast. Ultra cheap. Complex task? Full pipeline. Navigation, reasoning, interaction, execution. Takes time, but gets it right. And here's what you get. Reusability. Navigation module works across domains. You don't rewrite it every project. Testability. Test navigation independently. Test reasoning independently. Combine and test compositions. Explainability. If something fails, you know which agent failed. Not a black box, a clear failure point. Adaptability. Upgrade one module independently. Don't retrain the whole system. And the data backs it up. Compositional agents show 3 to 4% success rate improvements over monolithic approaches. Not huge, but consistent and reliable. So here's what to do. Map your task to sub-objectives. What sub-problems does your domain need solved? Design modules for each. Clear inputs, clear outputs, clear success criteria. Implement dynamic composition. Given a new task, which modules do I need? Build composition orchestration. Kafka can work, or a simple state machine. This is fundamentally how you scale, not by making agents bigger, by making them smarter compositions of smaller, focused agents. And by 2028, monolithic agent design will be seen as an anti-pattern. You want to be ahead of that curve. Now, before we talk about the learning roadmap, I want to address something equally important. There are skills you're investing in right now that have diminishing returns. They're not going away, but their ROI is dropping fast. And I want to make sure you're not spending 5 years optimizing something that'll be automated away. So let's look at 4 major areas where you should reduce your investment. Not eliminate, but reduce. Because capital, your time and attention, is finite. Every hour you spend on declining skills is an hour you're not spending on rising skills. And that opportunity cost? It's real. Let's dive in. Let me be specific about what's declining. First, manual prompt engineering. Today, you're investing 90 out of 100 points in this. Learning prompt tricks, jailbreak techniques, chain of thought crafting. It's a craft skill. By 2030, you need only 79 points. Why? Because reasoning models, O1, O3, are fundamentally different. They don't need elaborate prompts. They need simple prompts. And auto-optimization will handle fine-tuning. You'll spend your time building prompt libraries, templating, auto-optimizing, not handcrafting clever prompts. Time saved, 20% of your prompt engineering effort. Second, single-agent patterns. This is foundation knowledge. You still need it, but the ROI is dropping. Today, 85 out 100. Tomorrow, 83 out 100. Not a huge drop, but the energy is shifting. You're not writing papers about single-agent behavior anymore. You're writing about multi-agent coordination, about orchestration, about meshes. Third, protocol-specific expertise. I'm an MCP expert. I know React perfectly. I understand A2A intimately. That's great, but by 2030, these protocols are converging. There will be standards, and knowing one protocol deeply becomes less valuable than knowing all of them at a conceptual level. You move from MCP expert, protocol-agnostic architect. And finally, chain of thought prompting. Right now, let's think step by step is a powerful technique. It works. But reasoning models have this built in. O1 always thinks step by step. You don't need to prompt it. The model does it automatically. So your focus shifts from writing explicit COT prompts, observing and optimizing the reasoning traces the model produces. Now, here's the meta point. These 4 areas are declining not because they'll disappear, but because they're becoming commoditized, they're becoming automated, built into tools. So the competitive advantage moves up the stack, from how do I prompt this model to how do I architect intelligent systems at scale? And that's where you should invest your time. Not in mastering something that will be automated, but in mastering something that will remain human expertise for the next 5 years. That's strategic career planning in 2025. All right, so now you know what you need to learn. Let me show you when and in what order. I'm going to break this into 4 phases, and the sequencing matters. Some topics are foundational, others build on them. Phase 1. Now. The next 6 months. Critical foundation. In these 6 months, your focus is on immediate, high-impact topics. Agent runtimes. You need this first because it's the foundation for everything else, 6 to 8 weeks. Infrastructure bottlenecks. Understanding network and energy constraints shapes every architectural decision you make going forward, 4 to 6 weeks. Safety and guardrails. Before you deploy agents at scale, you need to understand defenses, 6 weeks. Observability. You can't optimize what you can't measure. Set this up now, 4 weeks. That's your first 6 months. It's intensive, but these 4 topics are prerequisite knowledge for everything that follows. Phase 2, months 6 to 12. High-impact infrastructure topics. Now, you're building on that foundation. Agentic mesh and decentralization. You understand runtimes. You understand infrastructure constraints. Now, learn how to scale orchestration, 8 weeks. Test time compute. You understand energy limits. Now learn inference strategies, 4 weeks. Agent identity and zero trust. You understand security implications. Now implement them, 6 weeks. By month 12, you've covered the 6 critical missing pieces. You're significantly ahead of 95% of the industry. Phase 3, months 12 to 24. Mastery and depth. You know the topics now. Time to go deep. Formal verification. You've seen safety problems. Now you prove they can't happen. 10 to 12 weeks. It's dense, but essential. Compositional reasoning. You've built systems. Now architect them elegantly. 6 weeks. Enterprise governance. You've learned technical architecture. Now learn organizational architecture. How do you structure teams? How do you own decisions? How do you scale? 8 weeks. Phase 4. Months 24 onwards. Continuous mastery. You're never done. This is maintenance mode. Multi-Agent Orchestration. You keep building, keep learning, keep optimizing real systems. Evaluation and metrics. You're always refining how you measure success, how you catch degradation, how you improve. Now, here's the important part. This is not a linear path where you finish one topic and move to the next. Topics overlap. While you're learning agent runtimes, you're also reading about infrastructure. While you're studying formal verification, you're also building agentic meshes. But the sequence matters. Don't start with formal verification if you don't understand safety problems yet. Don't study meshes before understanding runtimes. And here's my challenge to you. I've given you the roadmap, but execution is on you. Pick one topic from phase 1. Commit to 6 weeks. Deep dive. Build something. Don't half-ass it. And by week 6, you'll be in the top 5% of engineers who deeply understand this domain. That's the power of focused, intentional learning. So, are you ready to commit? Really commit? Okay, so the timeline I showed is the roadmap. But here's the actual curriculum. 15 chapters, 1 week per chapter. 15 weeks total to fundamental competency. Let me walk you through them. Weeks 1 to 3, test time, compute, agent operating systems, compositional reasoning. These are the foundations. Get inference strategies right. Understand runtimes. Design modular systems. Weeks 4 to 6, multi-agent orchestration, infrastructure bottlenecks, agent identity. Now you're thinking about coordination, constraints, and authentication. Weeks 7 to 9, safety, memory architecture, planning and reasoning. You're understanding defenses, continuity, and decision-making. Weeks 10 to 12, tool integration, observability, evaluation frameworks. You're thinking about interfaces, visibility, and metrics. Weeks 13 to 15, enterprise scalability, human agent teaming, formal methods and governance. You're scaling to organizations and proving correctness. That's 15 weeks. That's 3.5 months of intensive, focused learning. And at the end, you'll have depth across all 15 domains. You'll understand how they interconnect. You'll be able to architect systems that integrate these concepts seamlessly. Most people will never do this. Most people will skim topics, read blog posts, take a course, and call themselves experts. But if you commit to 15 weeks of deep learning, you'll be in the top 1% globally. Not the top 5%, the top 1%. And that's a competitive advantage that'll last for years. So, will you commit to 15 weeks? Let me share 9 patterns I've seen teams make, and I want you to avoid them. Anti-pattern 1. Assuming bigger model equals better. You spend millions on 70 billion parameter models when 7 billion plus intelligent inference beats it. Stop. Benchmark first. Anti-pattern 2. Monolithic agent design. One agent doing everything. It breaks under stress, it's hard to test, it doesn't scale. Decompose instead. Anti-pattern 3. Ignoring network bottlenecks. The network will be fine. No, it won't. By 2030, it'll be saturated. Design for edge constraints now. Anti-pattern 4. Treating safety as add-on. You build the agent, then add guardrails. Wrong. Safety is architectural. Bake it in from day one. Anti-pattern 5. Over-engineering prompts. You spend weeks perfecting prompt wording. Reasoning models don't care. Template, auto-optimize, move on. Anti-pattern 6. No observable agents. You deploy agents with zero visibility. Something breaks in production, you have no idea what went wrong. Add observability first. Anti-pattern 7. Assuming centralized orchestration scales. One coordinator for 100,000 agents. Bottleneck. Single point of failure. Build decentralized systems. Anti-pattern 8. Skipping formal verification. That tests are good enough. For critical workflows, they are not. Formalize, prove, then deploy. And anti-pattern 9. Ignoring organizational change. You build amazing technical architecture, but your organization doesn't change. Teams don't adapt. Roles shift. 60% of agent deployment value comes from organizational redesign, not technical innovation. So if you ignore it, you leave 60% of the value on the table. 9 patterns. Avoid them. And you're already ahead of most teams, because most teams will fall into these traps, and you won't. Alright, so you're going to spend the next year learning. But how do you know you're on track? How do you measure progress? I've designed the quarterly checkpoint system. Every 3 months, ask yourself, am I hitting these milestones? Quarter 1, foundational infrastructure. By the end of Q1, you should be able to explain AIOS architecture, not superficially. Really understand the kernel, the scheduler, the memory manager. Model a bandwidth bottleneck scenario. Know where saturation hits, how it impacts coordination. Deploy observability, real logging, real tracing, real dashboards showing agent behavior. Identify modular opportunities in your codebase. Which agents could be modules? If you hit these 4 checkpoints, you're on track. If not, you're not prioritizing correctly. Quarter 2, decentralization and coordination. Event mesh deployed. Kafka is running. Agents are communicating asynchronously. You've seen it work. Agent identity at conceptual level. You understand the IDs. You understand VCs. Maybe not implemented yet, but you get it. Inference strategies benchmarked. You've run 7B plus tree search against 34B baseline. You know your domain's trade-offs. Formal verification tools evaluated. TLA plus installed. You've read some examples. You're ready to learn. Hit these 4, you're significantly ahead. Quarter 3, safety and composition. Multi-layer guardrails implemented. Your agents have defenses, multiple layers. Tested against adversarial inputs. Modular agent architecture deployed. At least 3 specialized agents working together. You've seen composition in action. Formal spec written. For one critical workflow, you've written TLA+. The model checker has verified it or found bugs. Evaluation framework in place. You're measuring agent performance in production. You can detect degradation. 4 checkpoints. If you've cleared them, you're at the edge of industry practice. Quarter 4. Scale and governance. Double-digit agents running in mesh. 10 or more agents. Peer-to-peer coordination. Actually working. Organization redesign initiated. You've talked to HR. You've talked to legal. You're designing human agent team structures. Agent identity lifecycle operational. Agents can register, get credentials, have credentials revoked. It's working end-to-end. Continuous evaluation. Your system is detecting drift. It's surfacing issues. You're iterating based on production data. These 4 checkpoints, they represent maturity. Real, production-grade systems. Now, here's the honest part. You might not hit all checkpoints. Life happens. Priorities shift. That's okay. But I'll tell you, if you hit 12 checkpoints total across all quarters, you're on track. You're on the right path. If you're below 8, you're slipping. You're not prioritizing correctly. Recalibrate. This isn't about perfection. It's about progress. Intentional, measurable progress. And if you show up quarter after quarter with checkpoints cleared, you will absolutely crush it by 2030. Okay, you know what to learn. Now, where do you learn it? I'm going to give you a curated list. Not overwhelming, just the essentials. Papers. Read these. Infrastructure for AI Agents 2025. This is the paper that crystallizes everything we've talked about. Read it. A forecast model for AI-driven bottlenecks. Network and energy constraints explained with data. Inference scaling laws. Why smaller models with smart inference beat bigger models? Taxonomy of agent architecture options. Every pattern explained, every trade-off discussed. Tools. Build with these. AI OS, the agent operating system. Clone the GitHub repo, study it. OpenTelemetry plus Langsmith, your observability stack. Kafka and Istio, event mesh and service mesh. TLA plus and VLLM, formal verification and inference optimization. These aren't the only tools, but they're excellent starting points. Communities, join these. CNCF AI Agents SIG, Cloud Native Agents Working Group. Join the calls. OpenTelemetry Community, Observability Standards Development. Real engineers, real problems. W3C Decentralized Identifiers Working Group. DIDs and VCs, the future of digital identity. NeurIPS and ICML agent workshops. Latest research, cutting edge. These aren't passive consumption. They're communities where you contribute. Everything you need is available. It's not proprietary. It's not locked behind paywalls. It's just waiting for people like you to dive in. All right, I'm going to give you something. A 30-day challenge. 1 month, 4 weeks to start your transformation. Week 1, learn the landscape. Read the Infrastructure for AI Agents paper. It's dense, 2 hours. Watch free CNCF talks on AI agents, 3 hours. Then, sit down for 1 hour and diagnose your codebase. Where are your bottlenecks? Where's the complexity? Where would an agent runtime help? Deliverable, a 1-page architecture diagnosis. Where do you sit today? What's breaking? What do you need? Week 2. Build agent runtime and observability. Clone AIOS from GitHub. Deploy it locally. Run a multi-agent workflow. 4 hours. Set up OpenTelemetry plus Langsmith. Track traces. 3 hours. Instrument one of your agents. Log every decision. Visualize it. 2 hours. Deliverable, a dashboard. Showing traces. Showing the flow of agent decisions. Prove that you can see what's happening. Week 3. Experiment with inference strategies. Run a benchmark. Llama 7b with tree search versus Llama 34b baseline on your domain. 4 hours. This is critical. Use real data. Use real metrics. Measure cost. Measure latency. Measure accuracy. Implement one inference strategy. Maybe best of n. Maybe tree search. Something that works for your domain. 3 hours. Compare results. Which is better? Cheaper? Faster? Accurate? 2 hours. Deliverable. A detailed trade-off analysis. Cost accuracy graph. Your recommendation. For my domain, 7b with this strategy beats 34b because. Week 4. Design your agentic mesh. Sketch an architecture. For your domain, what would an agentic mesh look like? Identify 5 to 10 agents. How do they coordinate? 3 hours. Design identity. For each agent type, what DIDs would they have? What credentials? 2 hours. Threat model. What could go wrong? Sybil attacks? Impersonation? Data exfiltration? What controls do you need? 2 hours. Deliverable. A 5-page design document. Mesh architecture. Identity scheme. Threat model. Mitigations. 4 weeks. That's 40 hours of focused learning and building. At the end, you'll have 1 diagnosed problem statement, 1 working observability system, 1 benchmarked inference strategy, 1 designed mesh architecture. That's 30% of the way toward full architect competency. And here's the beautiful part. You didn't just learn, you built. You have tangible evidence that you understand this stuff. So, will you commit to 30 days? Just 30 days. 4 weeks. Then you'll know whether this path is for you. I think it will be. I think you'll get 2 weeks in and realize, this is the stuff that matters. This is what I should have been learning all along. So, are you in? We've covered a lot. From agent operating systems to infrastructure constraints. From inference scaling to decentralized meshes. From identity systems to formal verification. From compositional reasoning to organizational change. 13 months of learning. Distilled into 45 minutes. And here's what I want you to remember. You now know something that 95% of developers don't. You know that the future of AI isn't about smarter models. It's about smarter infrastructure. You know that by 2030, organizations without agentic meshes will be stuck. Organizations without formal verification will be vulnerable. Organizations without energy-aware systems will be broke. You know the inflection point. And you're in it right now. So let me give you 5 parting insights. 1. Network and energy limits will constrain scale by 2030. Not model capability. Not algorithm sophistication. Infrastructure. Design for these constraints today. 2. Agents are evolving from stateless apps to persistent OS-managed processes. Master agent runtimes. Containerize your agents. Treat them as infrastructure, not application code. 3. Centralized orchestration fails at scale. Trillion agent systems need decentralized, peer-to-peer coordination. Build event-driven meshes. No single coordinator. 4. Safety proofs, not just testing, will be required for regulated domains. Learn formal methods. Prove agent safety mathematically, not empirically. 5. Smaller models with smart inference beat bigger models. Stop scaling parameters. Start scaling compute budgets at inference time. This is both cheaper and more energetically efficient. Now, I know what you're thinking. This is a lot. Where do I even start? Here's my answer. Start with the 30-day challenge. 1 month. Read the papers. Build observability. Benchmark inference. Design a mesh. That's it. By the end of 30 days, you'll know if this is for you. If you should go deep on these topics. And I'm betting you will. Because you're the kind of person who takes 45 minutes on a Tuesday night to watch a video about AI architecture. You're curious. You're serious about your craft. You're willing to invest. And that's what it takes to be an architect by 2030. So here's my vision for you. In 5 years, you're not just writing agents. You're designing systems, architectural decisions, governance frameworks. You're the person other engineers come to when they need to think big. Your organization isn't struggling with agent deployment. It's scaling agent deployments. You've figured out the hard parts, the infrastructure, the safety, the orchestration. And you're doing it because you invested time. Not glamorous time. Not fun time. But deep, intentional, focused time on the fundamentals. The architecture of tomorrow isn't going to build itself, and it's not going to be built by people who are still optimizing prompts in 2030. It's going to be built by people who understand systems, who think about networks and energy, who design for scale, who prove safety, who architect intelligently. People like you. So, will you commit to this? Will you spend 30 days learning? Will you invest in the roadmap we've discussed? Will you become one of the 1% of engineers who truly understands AI architecture for scale? The architecture of tomorrow starts today, with you. And I can't wait to see what you build. Thank you.